Hello everyone. In this first video, we are going to review all of our different types of functional groups. Okay, so I do think that there's a reason to order them the way that I have in introducing them. Typically, you're going to be searching for a functional group in a very large molecule. So I think that it is easier to do a process of elimination. So the first thing that you want to try to find are any functional groups that contain only hydrocarbons, which are carbons and hydrogens. And the three types that we have are the alkene, the alkyne, and the aromatic. So remember that an alkene is going to be a double bonded carbon-carbon. Okay, and anything can be coming off of those carbons. And remember that any structure, we could also see it in a skeletal or in a condensed. So I'll stick to probably the expanded or the skeletal for the most part. Okay, so when you're looking at a skeletal, it may help to draw dots everywhere that you see kinks so that you know that there are carbons there. But what's important is that you have a double bond between two carbons in either case. Okay. Now, an alkyne is going to be very similar, except it's a carbon-carbon triple bond. And again, you could see the carbons, or the carbons could be hidden in the structure. And remember, triple bonds, anytime you go from a single to a triple, there is technically a carbon in between. So that would show 4 carbons in that case. And then an aromatic, those tend to be the big ones that can be easy to spot. It is a 6-membered ring with alternating double and single bonds. Okay, you can also have 2 rings that are fused together. Or 3 or 4, as many as you want. Okay, and that's still considered an aromatic. You can also have anything coming off of it besides an oxygen. So notice how aromatic ring without an oxygen atom directly attached. So I could have a chlorine coming off of this, could have some type of a nitrogen, or I can even have oxygens as long as they are not directly attached to the ring. So in this case, there's a carbon here on the ring, and then another carbon, and then an OH group. And so that is still considered aromatic. And the aromatic part is right here in the center. Okay, and of course you could look at it in the expanded version where you have carbons shown. Okay, where you have alternating double and single, and then all of those carbons could have something coming off of them as long as it's not an oxygen that's directly attached. Okay, next we have the haloalkanes, and for your textbook, I believe the word haloalkane is usually used, but there is an alkyl halide. Both names mean the same thing. So these are also pretty easy to spot. If you spot a fluorine, chlorine, bromine, or an iodine at all, that's automatically a haloalkane, and anything can be connected to that carbon. Okay, and then thiols, those are our sulfur-containing functional groups. And again, if you see an SH anywhere, then that's going to be a thiol. So the carbon could have anything attached to it as long as it has that SH group. Okay, and it's the SH group that makes it a thiol. Now we get into where we've got to start making decisions on our heteroatoms. With nitrogen, if you spot a nitrogen, you've got one of 2 options. Either it's an amine or an amide. So it depends on whether the carbon that is attached to the nitrogen has what we call a carboxyl group. So anytime you see this carbon double bonded to an oxygen, we call this a carboxyl group. Okay, but it does have to be directly attached to that nitrogen. So some examples of amines that do not have that carboxyl group would be if we had a carbon attached to anything other than a double bonded oxygen, and we have an NH2. Okay, we could also have that nitrogen attached to 2 carbons that are then attached to anything else, or we could have that nitrogen attached to 3 carbons. No more than 3, because nitrogen doesn't like any more than 3 bonds. Okay, and then of course those carbons could be shown in a skeletal form. So we could have the NH2, and I'm sorry, this should have an NH on it. We could have that NH2 with some skeleton coming off of it that has carbons. We could have a nitrogen with 2 lines, 2 different carbon groups coming off with a single hydrogen, or you could have a nitrogen with 3 groups coming off of it. All of those are examples of amines. Okay, now an amide, you would have to have the nitrogen directly bonded to a carbon that has a double bonded oxygen on it. Okay, so that's an amide. In a skeletal form, you would not see the carbon, but it is there. Okay, but it's the fact that the carbon that has the nitrogen attached to it also has a carboxyl group, a double bonded oxygen. That's what makes it an amide. And of course, that should be NH2. We could have that nitrogen attached to multiple carbons. So this will be my last example. We could have that nitrogen attached to 3 different carbons, as long as one of those carbons had that double bonded oxygen. Okay, now the last page is all about the oxygens. So when we are looking for functional groups in a large molecule, I always save the oxygens for last, just because there's so many options here. And when I spot an oxygen, I am going to ask myself, is that oxygen single or double bonded? And then does that carbon that has the oxygen, does it have 2 oxygens attached to it? Okay, and those are our last options. So let's start with carbon that is single bonded to an oxygen. So if you see a single bonded oxygen, you have 3 options. It could be a phenyl. And so a phenyl is where we have the aromatic ring with an OH group that is directly attached to that ring. Okay, now something that's not a phenyl that we saw earlier is if we have that aromatic ring and then off of it we have a carbon and then the OH. So notice how that alcohol group, or that OH group, is not directly attached to the aromatic ring. It is attached to a carbon that is then attached to the aromatic ring. Okay, so that is not considered a phenyl. Then an ether is going to be if we have the oxygen directly attached to 2 carbons. So notice how in this case the oxygen here only was attached to 1 carbon. If the oxygen is attached to 2 carbons on either side, that's an ether. Okay, and of course we could show those carbons in an expanded or in a condensed structure. And those carbons can be attached to anything. But it's the fact that on either side of the oxygen, we have 2 carbons. Okay, and then the last type of single bonded oxygen is an alcohol. And it's very similar to a phenyl, it's just that it's not part of an aromatic ring. Okay, so we have carbon that is bonded to an OH group and then whatever else is attached to it. Or as a skeletal structure. Right, we'll see that OH. But notice how that oxygen again is only attached to 1 carbon. Okay, so this is also an example of an alcohol. So technically you have two functional groups in this picture. Rather than it being a phenyl, you have an alcohol and then you have an aromatic. Okay, just a few more of our oxygen-containing groups. So next we're going to look at double bonded oxygens. So if an oxygen is connected, if it's double bonded to a carbon, it's either going to be an aldehyde or a ketone. So an aldehyde is one that comes at the end of the chain. That's where we have a carbon double bonded to an oxygen, and attached to that carbon needs to be a hydrogen. Okay, but of course, if we're in a skeletal structure, you're not going to see that hydrogen. It's just going to appear to come at the end of a chain. Right? We've got carbons, and then nothing past that carbon because the hydrogen is assumed. And then we could show the bond specifically to that hydrogen. So it could be C bonded to H, and then bonded to whatever else. But the point is that it is at the end of the carbon chain. Okay? And a ketone is going to be when that carboxyl group, when that double bonded oxygen is attached to a carbon that has carbons on either side of it. Okay? And then anything else can come off. So that's an example of a ketone. We've got a skeletal version of that. Again, notice how the carboxyl group has a carbon on either side of that double bonded carbon oxygen. Whereas here, we've only got one carbon attached. Okay. We think of the ketones as being buried. You can even have a ring. Right, and that's still considered a ketone because the carboxyl group has a carbon on either side of it. Okay, and then the last two are if we have both a double and a single bonded oxygen attached to the same carbon. So keep in mind that when we're saying check for double and single bonded oxygens, that needs to be attached to the same carbon. So again, we're asking if it's at the end of the chain. If it's at the end of the chain, we have what's called a carboxylic acid. And that is where we'll have a carbon with a carboxyl group and an alcohol all attached to that single carbon. Okay. And of course, we can have a skeletal. So double bonded to the oxygen with an OH group coming off of one end. And then anything else can come off the other side. But the importance is that double bonded and single bonded oxygen all attached to the same carbon and at the end of a carbon chain. And last one, we've got the ester. So an ester is when you have a double bonded oxygen to carbon. You've got your carboxyl group, and that carbon is attached to an oxygen, and then on the other side of the oxygen is another carbon. Okay, and then anything can come off of these carbons. But the importance is that you have both a single and a double bonded oxygen all to the same carbon, and then on the other side of the single bonded oxygen is another carbon. Okay. And then as a skeletal, it would look something like this. Again, oxygen with a carbon on either side of it. All right, so that introduces all of our functional groups. In the next video, we're going to go through how to look at different structures and decide which functional group that we have.